Hello. Let's wait 1 or 2 minutes for people to join and we'll get started. We are going to be solving LeetCode's weekly 360, which was a tough one, I'm not gonna lie. But we'll work through it and we'll try to think about how we would tackle these problems. So let's start from Q1. I'll share the link in chat. Farthest point from origin. It's an easy. You're given a string moves of length n consisting only of characters L, R, and underscore. The string represents your movement on a number line starting from the origin 0. The ith move, you can choose one of the following directions. So yeah, so these are wildcards in a sense. So if in the ith you move to the left if it's an L or if it's a wildcard, or you move to the right if it's an R or a wildcard. Hey NCC, how's it going? Yes, I'm gonna do it. Q4 it's a long one, so bear with me. But let's get the first 2 questions out of the way. Smart Coder, welcome. So we have to get the distance from the origin of the farthest point you can get to after n moves. We get a few examples. So this is very straightforward. So the only observations that you need is that you either want to move the farthest away from 0 to the right or to the left. And in that case, if you want to move the farthest to the right, you replace all the wildcards with movements to the right, and otherwise, if you want to move the farthest to the left, you replace all the wildcards with left movements. So, and the order doesn't matter. What matters is the counts, how many times. It doesn't matter if you make the moves in different orders. Your final position is determined by the counts of each L and R. So let's just count them. So we count the R's, we count the L's, and we count the wildcards. And we just return the maximum of 2 options. When we move to the left, we are going to move L times plus all the wildcards minus the right moves. And when we move to the right, we're gonna move R times to the right plus the wildcards minus the L moves. And accepted. So yeah, not much to add here. This was a simple one. Let me share my solution. Well, I mean, I guess it doesn't even matter, but for completeness, all right, so let's move on to the second one. So this one is it's a duplicate from a recent contest. So from exactly, I think it was the previous one, the 359, also Q2. It's the same problem, but the numbers are bigger. The constraints are the only thing that changes. In the other problem, n and target could be up to 50, I think. Sorry. And so here it's big, but when I solve this problem on stream, I solve it in both ways, the slow and the fast way. So the fast way works for this problem. So I'm not gonna dive into it. I'm gonna share the link to the video where I go over the explanation. So this is related to the trapezoidal numbers. So I give a very detailed explanation. So I recommend you to watch it if you haven't already, or if you don't know about those numbers. I try to explain them from scratch and their relationship to the sum of the natural numbers, the triangular numbers. And here, well, I mean, you can find the link to my solution in the description of the YouTube video. So I'm gonna code it up just for a completeness, but I'm not gonna explain much. So here we need to do mod, and we are going to use the trapezoidal numbers as we did in the previous one, which are a plus b times b minus a plus 1 divided by 2. And then we want to know what the b is going to be. The b as the parameter in the trapezoidal, the maximum number in the range, which is going to be either the minimum between n and target divided by 2. Yes. And then we want the sum from 1 to be inclusive, plus then we want to move from the target times n minus b. So n minus b are the ones that are left to cover. And if there are 0 left, if there is 1 left, we want this to be target. So the 1 is going to be cancelled with this 1. So this works. And we need to do the mod. And we're good. So this number can't be too big. I mean, it should fit in long in other languages, in a 64 signed integer, 64 bits. And we get the right answer and accept it. Cool. So yeah, watch that, please. I think the explanation was pretty good. If you want to know why this is the formula for the sum of the numbers from A to B inclusive. It was a visual explanation. All right, so let's go to the hard problems. Minimum operations to form subsequence with target sum. I'll share the link. You are given a 0 index. Oh, let me also share my submission for the previous one, because it's a little different than the one in the other contest. And okay, so Q3. You're given an array nums consisting of non-negative powers of 2 and an integer target. In one operation, you must apply the following changes to the array. Choose any element of array. Remove nums of I from the array. Okay, so you are splitting. So they are all powers of 2, so you can choose one and split it. One that is greater than 1, of course. And so the first observation is that the sum is gonna be constant. It's gonna be, doesn't change when we split 1 into 2. And you return the minimum number of operations you need to perform so that nums contains a subsequence whose elements sum to target. If it is impossible to obtain such subsequence, return 1. Okay. Subsequence is an array that can be derived from another array by deleting some of, well, this is the usual definition of subsequence. Yeah, whenever the problem involves powers of 2, usually it's a good idea to think about the binary representations of the numbers. So the order of the numbers in nums doesn't matter because whenever you have to find a subsequence, there's no restriction in the order. So you want a subsequence that adds up. So the sum is commutative, so it doesn't matter in which order they are. So that's the first observation, in addition to the one that we did. So yeah, one first observation is that if the sum of nums, like we said, it will stay constant, the sum of nums. If it is less than target, then of course we cannot find a subsequence that adds up to target, no matter what we do. And conversely, if it is greater than or equal to target, then you can notice that if we split them all up and we get all ones, then that's obviously going to add up to target. So that means that there is no solution if and only if the sum of nums is less than target. So let's get that out of the way. The sum of nums is less than target, then we return -1, and that is the only case in which we have to return -1. Then we were saying that we can represent this as a kind of multiset of powers of 2 by the exponent, by the exponent of the power of 2. So I'm thinking if I want to do that, yeah, maybe let's leave it open for now and think about the algorithm. So maybe we can work out one of the examples. One, 2. I should be able to copy paste this to the, can I do that? To the board? Okay, that makes sense. We learn anything every day. Okay, so we said, let's represent this as powers of 2, like we said. So here, so 32 is 2 to the 5, and these are 2 to the 0 and 2 to the 1. So we only need so 0, 1, 2, 3, 4, and 5. So we have 2 times 2 to the 0. So we put a 2 here. We have 1, 2 to the 1, 0, 0, 0, and 1. And then target, it's 12, which we can decompose it into 4 plus 8, which is 2 to the 2 plus 2 to the 3. So that means that we'll have 0, 0, 1, 1, 0, and 0. All right, so this is a simpler representation of the input. We haven't done much yet. We're just getting to the heart of the problem. So let's think about the, well, so this is from left to right, is the least significant to most significant. So let's think about this, the least significant digit first. So we don't have, so the number is not odd, right? It's even, it's 12. So we cannot use this, the ones directly, right? But we can, so we're gonna move on to the next digit, but in order to use the ones, we can join them in pairs to get a power of 2 of the next exponent. So here we have 2 ones, so we can join them and get 1, 2. Okay, so we can do this and add 1 here. Oh, yeah. So we add 1 here because we cannot use the ones directly. And this, notice that this is not, this doesn't cost anything because we're just joining things together. But you can think about having them separate if you want. We're just thinking about them in a group sense. That's why this doesn't cost us anything. And so we move on to the next digit, and we can do the same. But so what happens if instead of having 2 ones, we had only 1 1, right? What happens if this started as 1 1 and so on, and here we have a 0? Well, in that case, we cannot pair. We said that we wanted to pair the ones to get 2s, but when we have only 1 1, we cannot pair it. And notice that we cannot use this one because, again, this means that the number is even. And if you add 1, then the number that we get here is going to be odd, so it's not going to add up to target. So that means that we need to throw it out. And even if this was, it doesn't matter if it was only 1. If we had any odd number, so if we had 3, we can only pair 2 of them. We get 2 ones and we combine them as a 2, but we have to throw one out. So in summary, what we're doing is that we are shifting, since this is a 0, we're shifting, we're dividing this count, the count in 0, we are dividing it by 2 integer division, and that is going to effectively pair the numbers and drop the odd number out. Okay, so that is the case where there is a 0 here, but what happens if there is a 1? So if there is a 1, there are two cases. We either have already enough, we either have something greater than or equal to 1 of that power in nums, and in that case we just use it, we just subtract 1 to the numbers that we have here. This is not a good example because let me write it down here. So this is target and this is nums. So we're considering the case in which we have a 1, and here we could have, so this is not necessarily the beginning, right? This is the, let's say this is the ith position. So here we either have 0 or we have more than 0. Let's say that we have more than 0, then let's call this x. If we have, see, notice that this x also includes the ones that we combined from the previous. Okay, this counts everything. So if x is greater than 0, then we just subtract 1 so that we add up this power of 2, and we're done. We move on. We again do the same thing here to see how many we can move to the right. But what if x is 0? Well, in that case, we cannot pay. We cannot add up this power of 2. So we're gonna remember that as a debt. We have to pay this 1. So we're gonna move on, but we're gonna remember that we have to pay this 1. So eventually, when we have credit in some other position, let's call it J, when we get credit, we're gonna pay our debts. There could be more than 1, right? If we have a 1 here and all zeros here, and eventually we have a 1, but here maybe we have another 1 in the middle, we're gonna accumulate debt. Okay, so finally, when we get a 1 here, let me draw this again. So let's say this is I and this is J, and we had a 1 here, we had another 1 here, and so on. So we accumulated these 2 powers of 2 as debt. But now we found a 1, we have credit, so let's pay up. So now we do have to apply the operation of splitting. So that means that we can split this one into two of the smaller power of 2, and now we can pay this, and we can decrease this by 1 and have 2 here, and we have to continue and have 2 here, and now we can pay this. But notice that the number of times that we needed to split, which is the operation that is costly here, it was so this is not really a split. This is not, so we had to do 3 times. So it doesn't matter that we had one number in the middle. This is the one that defines the cost of paying our debts. So we only need to remember I here, which is the smallest number that we that we need to pay up. So maybe this is going to be clearer in the code. I didn't prepare the example. How do we know that splitting at this point leads to the optimum? Splitting at this point, you mean, yes, because this is the closest. We're paying our debts at the closest point that we find credit. So that is going to minimize the distance, which is how much we pay. And that's why it's optimal. And we are forced to do that because we cannot pay from the money that we get from the right. We always try to pay with the money from the lower exponents, because that's free. But if we can't, then we find the closest power of 2, and we only need 1 to pay all our debts, and that's going to be the minimum cost. I think this clarifies your question. So the code is not that complicated. The argument is more, makes sense. Okay, cool. The argument is more complicated than the actual code. The actual code is, I think it's pretty simple. So we're gonna keep track of the cost, the total cost. Then we want to keep track of the credit, and we want to keep track of the index of the debt. Remember that we only care about the smallest index of the debt that we carry. So let's say, so these numbers have up to are less than 2 to the 31. So that means that the highest power of 2 is going to be 2 to the 30. So we only need to go up to that power of 2 to the 30. So we're going to go from, like we said, from least significant to most significant. I is going to indicate the power. And so just to make this clearer, I'm gonna deal with the operation for getting the ith bit from a number. I'm going to encapsulate it in a function. This is pretty standard. We are shifting I places to the right, and then we're doing an AND with 1 so that we only select the ith digit, binary digit, the ith bit. And so how much credit do we have in the I position? On the one hand, we have the credit for, we can go over all the numbers and we can add up the ith bit. So that is all the credit that we already had, but there's some credit that we carried over from the smaller i's. So we're gonna add it up to what we have already. So that's our current credit. So we said that we first tried to pay our debts. So when do we pay our debts? When we need to have a debt index, which must be greater than or equal to 0. We use the -1 value as a sentinel for not having any debt. And then we need to have credit to pay. Okay? So let's pay now. So what is the cost of paying? It's the difference between the index I and the index of the debt, then we need to subtract the credit, what we used to pay the debt, and we want to remove. Now we are debt free. So now we handle the debt. Now we need to see if we need to handle the current power of 2 from target, and that is the case if it's on. And again, we want to try to pay it if we have credit. But if we don't have credit, we need to keep track of the debt. We need to add it to the debt. But we only add it to the debt if we are not already having debt. So if the debt index is -1, then if there is no debt, then we add the ith as debt because we could not pay it. And here we do what we said of dividing by 2 the credit, which is going to discard the odd numbers, and this should be it. One, 2, -1, and accepted. All right. Yes, I think I need to on my next streams, I'll try to prepare more examples so that I can explain the algorithm, because I'm using the examples. Hey, Warden, how's it going, man? Yes, join. I'm finishing question number 3 of the weekly 360. We're gonna get to the last one, which is a very nice problem. Let me put it like that. No, I mean really, I learned a lot from it. So, but it's hard. So, what I was saying is that I felt that that this became a little messy. I don't know if you could follow, but I'll try to come up with good examples to explain the algorithms in future streams, because I'm using the examples on the that are given on the statement, but sometimes they are not the best. For example, here I wanted to illustrate what happened when the number of ones was odd, but it was not the case in this example. So anyways, improvising that, I think, leads to some messy diagrams. So yeah, that's a note for myself. Let me share my solution. I think the solution is pretty simple. It's pretty quick, simple. I don't think you can do that it's as simple as it comes, I think. Yep. And I like the accounting metaphor. Sometimes it's useful to use some kind of metaphor for writing programs. Anyways, so let's go to Q4. All right, maximize value of function in a ball passing game. +1 to the use of credit debt concepts. Yeah, I think it's useful to organize your thoughts, to use some metaphor. Anyways, ball passing game. Well, talking about metaphors, this this is dressed up as a ball passing game, but I think it's kind of a distraction. Underneath is a very abstract problem. Anyways, you're given an array receiver of length n and an integer k. There are n players having a unique ID in the range from 0 to n-1 inclusive, who will play a ball passing game. And receiver of I is the ID of the player who receives passes from the player with ID I. Players can pass to themselves. That means that the receiver of I might be equal to I. You must choose one of the n players as the starting player for the game, and the ball will be passed exactly k times starting from the chosen player. And so here, I think this is more formally what you have to compute, including repetitions. In other words, so yes, this is so x is where you start the initial player, and then k is the number of passes. So yes, you are. This is called an iterative function iteration. So you can think about this array as a function that goes from this domain into the same codomain, and this is applying the function to itself k times. In any case, so your task is to choose player having ID x that maximizes. So this is repeating what, I guess. Return an integer denoting the maximum value of the function. Receiver may contain duplicates. Okay, so what are the constraints? There are up to 10 to the 5 players. And yes, this is what we said. And yeah, and k is pretty big, 10 to the 10. So how do we tackle this? So like I said, we are applying a function. So let's call it R from receiver, and they are using this notation, which means, for example, if k is 2, it means that you apply R 2 times to x and so on, and they also define k can be 0, in which case you just get x. So yes, if this is 0. But yeah, this doesn't matter that much. I think another way to think about this is as a graph, where every node has only one out degree, one out edge. So its out degree is 1, and it's given by R of x. And so it's easier for we programmers to think about this in terms of graphs, because we can use graph algorithms, because we are essentially asked to find a path starting from any node and having length k. Okay, so since every node has only one edge going out of it, then once you determine the initial node and the length of the path is already determined, okay? So one solution would be to just try all the nodes as the starting node and then go over k steps, move forward, and add up all the values of the nodes, and finally you get the maximum. All right, so we have a solution, but the problem is that k can be up to 10 to the 10, so that's going to be too slow. Okay, so what do? Maybe we can think of a clever way. So this path obviously is going to repeat nodes, right? Because k is very big, it's much bigger than the number of nodes. So if you visited in your path n plus 1 nodes, then there must be a duplicate, okay? Because there are at most n nodes. So maybe we can do something clever, and we say, okay, we move forward in the path until we find a duplicate. So that means that we find a cycle, and we do something clever, and we figure out what the sum is for that path. Well, turns out that doesn't cut it either, because that would be quadratic. That would be O of n squared, because we're trying every node and then we're moving roughly n steps, and that's too big because n can be up to 10 to the 5. So it's better because this was 10 to the 15 if you include the number of nodes, but it's still too slow. It's 10 to the 10. All right, so I think this motivates what we need to do. So we can keep the idea of trying every initial node, but we need to find a better way to compute the sum of the path. A quick way. It has to be less than linear in terms of n. Strictly better than O of n. So to be clever, getting a bit lost. Can you also explain summary of the problem statement? Okay, so I translated the problem statement into a graph problem. So I don't think it's useful to go over the baseball analogy here. So we are given this array that represents a function that for every node, let's call them nodes instead of players. For every node, we have nodes, well, let's call them U. The nodes are all the numbers in this range, and we have this function that gives us a B, and you can think of this as a directed edge. So this is U and this is B. Okay, so what I said was that given this representation of the graph, every node has exactly one outgoing edge. So that means that if you start walking, or if you start a path from a node, for example, from U here, it is already determined there's only one successor, one way to go. So so they are asking you to choose one node where to start your path, and then move k times, and add up all the labels of the nodes. For example, u plus b plus c, and maybe then you go back. Okay, and you do this k times, and that gives you the value when you start from u. Okay, u determines the path because k is constant, and this is the value associated with u, and you need to find the maximum of these values. Are you following the? I think we can abstract the baseball metaphor at this point. A path of k starting from any, then. Yeah, path of length k, well, yeah, length k edges. So, going back. So, like I said, we can keep the structure of the algorithm as trying every initial node and then trying to compute quickly what's the sum of the path starting from that node. But to do that quickly, we need to be clever, and we need to understand the structure of this kind of graph. So this kind of graph is called a functional graph, because, like I said, it's defined by a function. So the condition for functions is that you have only one value for every value in the domain. But we don't care about the functions, actually. We want to understand the shape of this graph, and the shape is pretty interesting. Notice that when we start walking, like I said, we always end up in a loop. We always repeat a node. So the paths, when we start somewhere, we're gonna be moving from nodes, and eventually we're gonna go back to a node that we've seen. It could be that this node is already in a cycle, in the cycle, and the graph doesn't have to be connected, right? It could have different connected components, and it also can have, like it says in the statement, it can have loops, which sometimes is forbidden in some graphs, but in this case, b can be equal to u, so you could have a cycle of only one node. So when you observe this, one way to think about the structure of the graph is that let's think about one connected component. So it's going to have necessarily a cycle. Okay, this curly line it means that this is a path, not just an edge. I'm drawing 3 nodes in the cycle, but we know that it could have from 1 to any number of nodes, but it could be 1. And then we have from the cycles, we have trees. Okay, so because like we said, we can start from here. Yeah, one way to think about this, since every node has only one successor, you can think of the successor as the parent, and that's how you get trees. You could have this like this. Yeah, here, whatever. So and you can also have nodes. So this is also called a pseudo tree, or well, if you think about all the connected components, you can, it's called a pseudo forest. So the structure is that you have like this center. You can think about the as a center, and then you have trees that have the nodes of the cycle as roots. So why can't you have a cycle here? Well, if you connected any nodes here, it would mean that you have one node that has more than one successor, but that cannot happen. Okay. So this is very important. This is the structure of the graph. And so now we can think about a strategy for computing the sum quickly. So we can handle first the cycles. So cycles are circular arrays. So, well, first of all, how do we detect cycles on a graph? So that's the usual way is with DFS. The way that I know when you have a directed graph with more than one connected component, possibly, I use the algorithm from CLRS, from the Corman book, where you paint the nodes. Initially, they are all white, and when you open a node, when you start the recursion for some node, you paint them gray, and then when you close them, you paint them black. And if you find any adjacent node to the current node that is gray, it means that you found a cycle. If it's black, it's not a cycle. And if it's white, you have to recurse to that node, etc. So anyway, that's a standard algorithm. I'm not going to go deep into that. And so once we have identified the cycle, then you can think about the cycle. It doesn't matter, as a circular array in a sense, right? So you have a cycle which has values u. So let's say u1, u0, u1, so on, and u s minus 1, where s is the size of the cycle. Okay? So this is just an array, but it's circular in the sense that you wrap around. That's why it's a cycle. So now the problem boils down to finding a range sum in a circular array, right? Because that's what they are asking. So we can start from any of the nodes in the array, in the cycle, okay, for example here, and we want to sum from this position k times of a range of size k elements, but with wrapping around. Okay? So how do we do that? Well, as usual, we can try to solve range queries, range sums with prefix arrays. But here, we first need to know how many full turns we're going to do. So if the number of nodes is k and the size of the cycle is s, then we can divide. So we can use this divmod function, okay, for k divided by s, the size of the cycle, and this is going to give us two numbers, right? The quotient and the remainder. So that means that we are going to do q full turns in the circular array, and then we are going to have this remainder starting from here. So we need to quickly, this array can be big, it can be 10 to the 5, so we cannot go over it. We said that we needed to do this quickly. So we need to quickly, so now we reduce it to a number r, which is, it's smaller than s. It's from 0 to s minus 1 inclusive. So this is a simpler problem, and one trick to do this is to have a prefix sums, which is going to start, let's say that we have a 0 at the beginning, then we're going to have u0, then we're going to have, well, u0 plus u1, and so on. A typical typical suffix array, but just to deal with the wraparound, we can duplicate the array. If we have 2 times the same array and we compute the prefix sums, then when we add r, we're going to stay inside of the array, and that's going to be useful to do this. So, and then it's just a difference, just like we always do range sums with prefix sums. By duplicating the array, we get rid, and doing this division, we get rid of the wraparound issue, and we just apply range sums with prefix arrays. Okay, so we found it. We found a way to handle cycles quickly in constant time if we compute this prefix sums, but we have to compute the prefix sums for the whole cycle, and then we go over the nodes and we use it. So that's not a problem. Okay, and now we need to handle the other nodes, the ones that are not in cycles. And as you can guess, cool trick, yeah. Yeah, I haven't used this that much, but I think, but it's pretty useful. Yes, that's why I said that I learned a lot from this problem, because I refreshed some ideas that I haven't thought about lately. Well, well, how do we handle the nodes that are not part of a cycle? Well, like I said, these are trees. So we can try to traverse the trees with a DFS algorithm, for example. And the thing is that we want to traverse them. We want to start from the root. But notice that so we traverse trees from the root, but notice that the edges go the other way. So we can create another graph with the edges turned around, and we can traverse it from the root and try to compute for every node this sum, the sum starting from that node. And now you're going to understand why it's useful to traverse it this way, because if you start from this node, for example, so you want to move k times from here. So that means that you first are going to move in this path, the path to the root of this tree, and then you're going to enter the cycle, right? And then you're going to go over the cycle, which is something that we already know how to solve. So we only need to keep to find a way to add this up, right? So if we go over the if we go this way, that means that we can keep track of the sum of the values in the path, and then we know how many nodes it has, so that we subtract this from k, and then we pass that number to this cycle. So we know that we start on this node, and we know that we subtract these two nodes from k, so we know that we're going to do k minus 2 steps starting from this node. We already know how to solve this problem, so we combine both things and we solve it. But there is a catch. As if this was not enough, there is a catch. Maybe there's a simpler way to solve this problem, but that's what I did, and it worked. I don't think I could have solved this during the contest. Anyways, well, because the other problems were also they were also a little tricky, so I would need time to make this work. Anyways, so how do we do? So what's the catch? The catch is that k could not, the path could not reach the root. It could not include all the nodes outside of the cycle in this path. So that means that we need to quickly add up the nodes. So let's say this is the node in the cycle, right? This is the node in the cycle, and then we have all the nodes here in this path. But let's say that k is 2, and so we're traversing this tree. There could be other things here, right? But it doesn't matter. We're considering this sequence, this path. And so if we are considering, well, I guess this is the best example. If we want to compute the sum starting from this node, then since k is 2, well, remember that k was the number of edges, but I think it's easier to think in terms of, at least for me, it's more convenient to think about the number of nodes. So let's change k, let's increment it by 1 so that k is the number of nodes. So here, if k is 2, that means that the path is going to be this only. So how do we add up this quickly? We cannot just add all the nodes in the paths, because here we only need these two. So again, we're going to use prefix arrays so that we keep track of all the prefix sums, and then we add this node, the sum including this node, and we subtract the sum in this node, and that's how we get this, and so on. So yeah, that is all, I think. Let's start to code it. Bear with me. It's not easy. Let's see if we get it right on the first try. All right, so yeah, let's do the adjustment on k. So k is initially the number of edges, but we want to think about the number of nodes in the path. So let's increment it. So what do we do first? We need to detect the cycles, and like I said, we use DFS for that. And I'm going to just do a standard DFS. This is not necessarily a connected graph, so I'm going to color. Hey, Jabra, thanks for the follow. You're doing it the chat way. What do you mean? I don't know if it's solutions. Oh, they cheesed it. There was a cheesed solution. Okay, I'll look. I didn't lately. I'm not looking at other solution. Maybe I should, but I try to come up with this on my own. So that I give my personal take on this. It's more impressive. Yeah, it's not my goal to impress. It's had the algo memorized. Yeah. I think the advantage is that if I really think through it and work my way up to a solution, then it's easier for me to explain what my thought process. Whereas if I use something from someone else and I didn't think it through, then it's harder to explain how to come up with it. Anyway, so yeah, this is standard. Okay, so we're going to color white, gray, and black, which are, in computers, we represent that as numbers. So 0 is white, 1 is gray, and 2 is black, because that's the way computers are. Anyways, well, anything in the world can be modeled by numbers, but that's another, that's a philosophical discussion. Anyway, so again, so this could be it could have more than one connected component, so that's why we need to do loop first, and then we run the recursive DFS only if its color hasn't been visited yet. So it's colored white. Here we want to call this function, and here we want to implement DFS visit. And okay, when we open the node, we color it gray. In the end, we color it black. And here, there's only one adjacent node. We might be able to do this with a loop, but I think it's easier to just code the standard DFS. And so we have only one adjacent node, the successor, which is B. And so if the color of B is white, then we just visit it. But if it is gray, then we found the cycle, and we want to get that cycle somewhere. We want to save it for later. I'm not gonna do the process in here. So let's have something to store the cycles, and we append the cycles starting from U or B, it's the same. All right, so we're gonna need a cycles array, a list of lists is going to be, and then we wanna get the cycle from the start, and we're gonna go. So I don't know why Python doesn't have do whiles. I end up doing hacky do whiles, but they should. So here it's easier to have a do while because we have a node that is going to be the beginning of the cycle, so we always want to add that to our list. And then we don't want to, if we move on to the next, if we get to the start again, we break. So that's why I think it's more convenient to have a do while here. Anyways, And yeah, and it might be handy to know whether a node is in a cycle or not. I think we're going to need it. So let's also in cycle, and here this is true. This loop goes over all the nodes of the cycles, and this is going to go over all the cycles in the graph and so on. So good, we have found all the cycles. We are making progress. So here I think I assumed that there was an n variable, but I haven't defined it. Receiver, I write received. Okay, so we have the cycles, cool. So now we want to, we're gonna keep track of the best sum so far, 0. I think you can always do 0, get 0. Yes, k is at least 1, so you can always get even n minus 1, I guess. So 0 is a good starting value. You should never get 0 as an answer. So we're gonna go over the cycles, and we are going to compute the prefix sums, which is a standard code. The only difference is that we're gonna duplicate it. So we're gonna do twice the length, and the value, so yeah, let's call this u, which is the convention that we're using for the labels of the nodes. So cycle is going to be I mod the length of the cycle. That's going to be our value in the duplicated list. And here we do the usual, we append the last element plus the current value. So now we have our prefix sums that could handle wraparound. So we want to go over all the nodes in the cycle, and here is when it will be handy to have a function that can compute the what we said, that can do all all that we explained here, the deep mod and all the prefix sums. So let's write that function to encapsulate, because we'll have to reuse it in two times. So here, let's call it range sum, and it's going to get the prefix sums array that we computed, and then a starting node, a starting index, not a node. There's a small difference, because a node is one of the labels from 0 to n minus 1, but this is an index in the cycle. And then we want the count of nodes, right? That's what our range, we represent the range as a starting point and a count of elements. And so we need to know the size of the cycle, and we can get this. Remember that we added a 0 to here at the beginning for convenience, and then we duplicated the node. So the size of the cycle is going to be the length of this, okay, because of how we constructed it. This is going to be the size of the cycle. And now we use the deep mod that as we showed. And k, our k here is count, is the number of nodes in our path. and in a range, the number of elements in a range, and then the size of the cycle. And so Q is the number of complete turns, but how much does a complete turn sum? Well, is the prefix for size. Okay. We added a 0 element, so the index represents how many elements it has. So size is correct for this. This is going to give us the total sum of the cycle. And then we want the difference from the start plus R minus the prefix from the start. And this is all. It's pretty simple, actually. So now first consider the let's first consider the sum starting from the node within the cycle, because we already have the function ready. So we want to do the range sum for pref, and the index is I, the start index. So this is start, and this is count is k. Okay. And this is going to handle all the nodes in cycles. But now we need to do the traversal of the trees starting from the nodes of the cycles. But what we said is that we needed a graph, what that was the inverse of the original graph. So let's create the adjacency list for it. So this is pretty simple. From the receiver of U, we want to add U. Okay, this is the edge turned around. So now we can use that to traverse the trees from the roots. But we need to start, we want to start from the children of the roots. That's gonna be more convenient because we don't want to count in our first calculation. We don't want to count the cycle. We already count the cycle with this function. So we want to start from the children. So let's go from the adjacent nodes of U, and we need to take care of not getting into the cycle as well. So that's why we computed the in cycle. So if we are not in the cycle, we are getting out of the cycle, and we are going to do another traversal from B, and we are going to keep track of we're going to create another prefix sums array, like we said, but this is going to be changing depending on the traversal. This is another DFS, but I'm calling it differently. But I could call it DFS, but we need a different implementation, I think. Anyway, so this is going to give us the best, the maximum. So we just need to update our maximum here. But we also, when this computes this is going to compute the value of the path from the current node of the traversal to its root, but then it will go over the cycle. So we need to give it the information to do that. And what we are going to do is just, so the information that it needs to call range sum, right? Range sum needs the prefix and the start and the count. We already know what the start, we already know what the prefix is for the cycle, which is this pref. And we already know the index of the current node that we're considering in the cycle. But then we don't know the count, but because the count is going to depend on the depth of the node in the traversal. So let's do a partial evaluation of this function range sum. The range sum, we give it pref and we give it I, and then it will get a function that only needs the count to compute the cost of the sum of the path. Okay? So that we don't pass anything that we don't need. So finally, we need to do the traversal. We need to do it after the adjacency list because that's what we need to use. So we traverse and we get the current node, the prefix sums, and the range or the cycle, the cycler, I don't know, whatever we want to call it, cycle sum, other. No, cycle sum. I like cycle sum. Okay, so then, okay, so initially, like we did with the other prefix sums, initially we want a 0 for convenience, but now we are at node u, so we need to add u to the sum. So we append, we do the same thing we did before. The last value, we add a new value with the last value plus the new value. And at the end, we want to pop it so that we keep track of the path to the node even when we backtrack. And we're going to have a current result. We are going to go over, this is the usual DFS stuff. We go over the children, and each children is going to have a vest result, and cycle sum. Yes, summer. So this seems like the sum itself, not a function. That's why I preferred cycle other. But what would be the word for sum? Anyways, so now we need to calculate the sum from node u. Okay, how do we do this? Well, let's get the def first. The def is the length of the prefix minus 1, right? Because we added the 0, remember? And then let's first calculate the this. Okay, this sum without the cycle. The part without the cycle. So let's call this the head. And this is going to be, like I said, a prefix sum from def or from the last element minus, and here we need the def minus, yeah, maybe it's clearer here if I put def, no. Yeah, def minus 1. Yeah, that's right. So def minus k, right? So for example, if k is 1, we want this to be 1 less than this, because that will only add u, so it makes sense. But what happens? K, in many cases, it's going to be greater than def, so this is going to have a negative array, a negative index, so that's gonna throw an error, or, well, I guess in Python it will break silently. So we usually use the streak of max 0 and the number that could be negative so that we saturate at 0. And finally, so we already have the head. Now we want the cycle. So for that, we're gonna add this to, yeah, maybe we don't need to have that variable. And so here we use our cycle magical black box, and we need to know what the count is. So it's going to be k minus the depth, because we need to subtract that. The depth are all the nodes in this part, and only after those nodes we get to the cycle. But so this is the extra steps that we're going to make, or the steps that we're going to make on the cycle. But this could again be negative, and that will break our code. So if we pass count 0, then cycle adder will give 0, so it makes sense. So let's again use this trick. And now we have the value for node u. And then we update it with the values of the other nodes. And I think this is the whole thing, right? Let's see if it works on the first try. Runtime error. Yeah, usually I have some typos. So here I confused else elfie instead of elif. That's okay, 6 and 10, and let's accept it. Cool. Yeah, that was quick. I mean, in terms of the number of runs. So yeah, I hope you learned as much as I did for this one. It was a cool one. It was hard to get during the contest, I think. I don't know how it can be cheesed. I'm interested in knowing how we can cheese this one. But I think this is solid in terms of complexity, and I mean, it might be possible to do this simpler with simpler code, simpler algorithm, but I think it was okay in the way that we organized the code. So let me share my solution. Very cool. Yeah. Thank you. Let me know if there's some step that you want me to go over. So this is my submission. If you're interested, what else? Did I share my solution of the previous one? Yes, I think I did. So yes, it's been an hour and a half. That's okay for this contest. I said it was the hardest. I don't know if you agree, but I think it was at least the hardest in a while. So yes, that's all I have for now. I'll upload the YouTube video, so if you're seeing this in YouTube, please subscribe to my channel, click the bell button like they say. Hey, NCC, thank you for the support. Check out the binary lifting way too. Oh, there is a binary lifting way? Haven't thought about it. Yeah, I guess I'll try to find other solutions afterwards, but maybe I'm not that motivated after I do the stream. But yeah, so thanks a lot, guys. Maybe I can rate someone. I haven't been doing that lately. Do you have a suggestion? I think Chichi is streaming. So yes, I'm gonna rate him. Yeah, Uncle Cheech. See you, Lucia. Thank you. So how is this done? I think it's this way. Thank you, guys.
This is described in 2 lines. A of P of Q of I. Hey, welcome back, lead coach. Welcome, welcome.